Man will sit down.
You guys should have finished the garbage collection assignment by today, which is great because this is when you finally have a completely working implementation of meaning back to front. Okay. I think you should have visited quite so lately. I think Fini is actually not a bad language. I think it's a lot. And I think it's a lot better than a lot of languages that you currently use. Actually,
The bar is low.
Yeah. So, like for example, I heard someone just mention Python. Python doesn't have a compacting garbage collector. It has a reference counting collector. Even worse than that, the semantics of the reference collector leaks out. So there are some Python programs that won't even run unless it has a reference counted collector.
Oh, you can fake everything.
Yeah. So, you add strings, you add characters, booleans, and Fini has basically the same features as all these other scripting languages. And it will be fast, especially after you do your JIT. Okay. So last time I made a joke about how you never finish a garbage collector. The real joke is that you guys think it's a joke. Right, so this week's assignment is the tag primitives optimization. So now we're on to the optimization half of the course. The tag primitives optimization is supposed to be, if you do everything right, like a 20-minute half. Okay?
That's all right.
It really is.
Some people have already gotten it done. If you happen to have this one dangling little bug in your garbage collector that somehow wasn't tickled yet, then putting this to someone tough might tickle it, and then it'll just really confuse you. So if you implement it and things don't seem to work, make sure you also consider your garbage collector, because things just keep on coming out. So when you do your JIT, that's going to interface with the garbage collector. When you define an FFI, it's going to interface with the garbage collector. If you want to add threading, it interfaces with the garbage collector. If you want to implement hash tables, it even interacts with the garbage collector. So basically, from here on out, everything's considering the garbage collector. And that's what I mean, like, you're never done with this. Okay, so next week is the tag primitives assignment. And then after that, we'll be doing code generation.
So you did something which I do sometimes, but I always try and point out when people do it, which is confusing a language with its implementation. There is this phenomenon in computing, which I have observed over the last number of decades, that a language always gets labeled with the properties of its first implementation. Right? If you make it slow, everyone will go, language is so slow. It's really hard to turn people around on those things. Right. So fast, slow, that's not a language feature. It's an implementation. So now you've got working Fini, you can do major programming projects. Okay, so today we're going to close up on interpretation. This will be more or less it for interpretation. So there's some material on a bunch of techniques which, if you are faced with the situation of having to build a fast interpreter, which sometimes happens, some of this stuff might be useful. And then we'll start on compilation proper, and there'll be an introduction to compilation techniques, which hopefully will set you up for kind of the big exercise, which is coming up, which is to build the JIT for your system. So that's the goal there. Let's see how we get on. Okay, so actually, out of curiosity, does anyone have in their heads sort of speed-up factors of their implementations as they've evolved? What did you go from AST to bytecodes? How much did your GC slow things down? Any optimizations? Anyone care to volunteer any numbers from their heads?
4x.
For
Initial to current.
4x. Okay. All right. Okay.
6x or so.
Okay. Anyone get as much as 10? Really? Okay. Okay. Cool. Well, we'll see what you get from compiler. Okay, so as you've probably discovered while you've been debugging, there's a lot of overhead as well. There's you fetch, decode, dispatch, bytecodes. I was going to put up a stepping through a sequence, but you've probably seen this so much you don't need this anymore. So, it's a lot of overhead, and in some situations you actually do want faster interpretation. When we talk about tiered compilation, which will be probably next week, you'll see the first level execution mechanism, while it's not critical, can be important on performance. So, having a fast interpreter can be significant. Also, if you don't have the opportunity to compile, either because you have resource constraints where you can't generate bulky code, or you have environment constraints that preclude that. So you may be running on a system where you're not allowed to generate code, right? For security reasons, you don't get writable text. Then you want to make your interpreter fast. And there's a whole bunch of techniques. I'm not going to attempt to go exhaustively through the literature because there's a lot of it. And frankly, as you get to the peripheries, you get to the kind of, does this really matter, a few percent in an interpreter, when you can get, factors, integer factors by moving to compilation. So, but I'll give you the main things, at least the ones that I think are the significant ones, and try and tie them together. And some of this stuff is relevant for compilation too. It's helpful to know one before you go into the other. So the first technique I'm going to describe is threaded code. And the idea here is very simple. Instead of doing fetch, decode, and dispatch to your routine, you do that once, and then you just store a pointer to the thing you're going to. So you don't have to do the decode. It's already decoded. You already have an address. So there's some amount of expansion factor in this, usually, from bytecodes to machine addresses. But might not be that much, might not be punitive. And there is usually a pretty significant improvement in performance. The technique is really old. The first published description goes back to 73. One of these, if you don't look at CACM papers from the 70s, you should. People wrote in a very different way back then. I think this is like 3 pages long or 4 pages long. It took me about 10 times reading it, figure out what he was trying to say, because there are all these examples in machine code you don't know. For a source language you don't know. Using terminology that's long past. And it was actually originally a technique for a compiler. This was done in the context of a Fortran compiler. And the idea then was, because of the machine architectures, it was actually pretty competitive with direct compilation back then. That's no longer really true anymore on modern architectures, but nonetheless a fascinating read and a short paper. So the idea here is we're going to do this transformation. Here's a sketch of some bytecode program mnemonic terms, right? It's really bytes in memory. And here's the sketch of what your loop of your interpreter looks like as you currently have it. And what we're going to do is we're going to transform this into a bunch of addresses of routines. And one of the things about this section is it's very, very hard to express most of these techniques in even C. As low level C is as a high level language, it's still not low level enough really to capture some of the ideas. So I'm going to use some assembler here and there. I've tended to use sort of Spark because I'm familiar with it, but it's kind of generic RISC assembler, so it shouldn't be that hard to follow. If there are any mnemonics I've used or any conventions that don't make any sense, please stop me and ask. Okay, so we go from bytecodes to addresses, basically pointers to code. And here's an example of in this particular case, we still have our interpreter loop. So our interpreter loop now, our target is a register that contains a pointer to the thing we're executing. So it points through here. This is now our PC. Previously we had a PC that was stepping through bytecodes. Now we're stepping through these machine addresses. So each one of these is a whole word in size. We're going to have this thing, our target, that's pointing through there. And what we're going to do is we're going to load it and then just jump through it. And at the far end of that, after we've done the work part, which is I've elided because that's not important at this point, we just increment the thing to the next word and jump through that. So you can see there's a lot of stuff that's simplified. We can go fairly trivially even further and eliminate the loop entirely by just copying that code that was in the loop to the end of the loop, right, and put the increment and the jump there, and then each routine is just fetching, decoding, and jumping to the next one. And in fact, in the original paper, that was just one instruction anyway, so copying it didn't really matter where you put it at the beginning of, or at the end of one thing or at the end of the other. It was the same cost.
Why is this called threading?
You don't thread.
You kind of, yeah. It's a use of the word that predates the modern use by a lot. So this has the dibs on the word, but it's sort of fallen into disuse.
Okay.
And if you think about, well, you'll see when I've got a couple of the pictures from the original papers later, you'll see it sort of looks like you're sewing a thread through all the action routines. Okay, so that's pretty straightforward, but we can go even further than this. So in this case, we're just, we point to the first thing we're going to execute, and then that'll figure out the next thing and jump to that, and that'll figure out the next thing and jump to that, etc. Yeah, so on a CISC machine, as in the original paper, this sequence of add, indirect load, and then jump can be expressed usually as a single instruction, and that's how it was done in the paper. I think it's a PDP-11 instruction in the original paper. It's just one instruction. So, and you know, one instruction is one instruction, or at least it was back then. It was pretty inexpensive. You could put it anywhere, and it was more or less the same cost as doing something simpler. Back in the days before pipelines. Okay, so these are the pictures from one of the original papers. This is actually from the next paper I'm going to mention. But you can see in the original scheme there's our loop, which is going round and round, except at the bottom of the loop it jumps off, does something, comes back to the loop, jumps off, comes back to the loop. Whereas in this scheme now, we're basically just threading through all of the routines using, in the example I showed you, a data address, which we're then using as a branch target. And for the modern micro architectures, this thing's basically kind of impossible to predict, really. And these things now become hard to predict because now we're threading through. You know, if we're not going through a loop, then each time you call an action routine, the following action routine it calls is going to depend on what the next bytecode was. So it's just going to go all over the place. So and you know, these are shared amongst. So this is a description of an add. This is all the adds point to this add. So that branch at the end is going to be used for every add in the program. So it's going to be very, very hard to predict. There is a modern trick which we can employ to make it a little better, which is to replace the addresses here with calls. And that has a couple of good effects. The first is now we're actually executing through the thread, not just fetching data and using that as a target for an address, which means a predictor is going to have a much easier time, certainly going to should be doing really well on these. And rets usually are very well predicted too, if you've got enough work for them to do in here, because usually there's a kind of a longish gap between you know, where the thing is really executing and where it's fetching. But this certainly makes things better on most modern architectures. So we're just aligning now our PC. We're just using the native PC to model that and executing directly. In all of these cases, where we're doing the threading at the back end of the action routine, we have to do some amount of deviousness to implement branches. In this case, the naive thing is to manipulate the return address. But instead, the generator of this code can generate jumps, right? We're now in this kind of blurry line between interpretation and compilation. Is this an interpreter or is it a compiler? You know, and if you think this is a compiler, where did, you know, so raise your hands, who thinks this is compiled? Where did we cross the line?
You have to know the ISA to be able to do this trick, right? You wouldn't be able to do this in C.
Well, you have to know the ISA to write assembly code.
I mean, that's true.
Right, so where did we go? But, you know, is this a compiler? I would have said not, right? This is just data memory, right? There's no new instructions being generated here. This can be, all this code can be in a read-only text segment. This has to be generated as data. I would say that's not a compiler. That one I'm not really sure about. And that one, the last one, does seem like a compiler now, but it's kind of a blurry line. And if you look back at the original definitions, when I was guessing at definitions for an interpreter, there's this other definition, which is an interpreter does the same thing for each thing being interpreted. By that definition, this is an interpreter, because the same action routine is being executed for every add in the program. We're not doing anything different to any of them. So it's a really good example of how blurry the grey, the black is and the white, where they meet the grey boundary.
So is the slowest instruction here the red? It's the only thing that,
Well, that's very microarchitecture specific.
because everything else seems pretty easily predicted. Right?
Well, this is easily predicted using a return address stack. Right? If you're pushing, if the fetch pointer down here is able to grab, you know, the pushed return address through some bypass and feed it into the fetch unit before you've actually drained the pipe of whatever's in here, this will go really quickly.
So then it begs the question, why is the compiler of the JIT, why are we able to take advantage of this for the compiler of the JIT, as opposed, like the example where you have like a subroutine, it's assembly, another subroutine is assembly, why are we able, what's the performance improvement that we get there that the compiler of our interpreter could not have done?
Oh, where did, okay.
Yeah, where are we drawing the line between?
All right, so in the first case, if you look at this case, we're fetching bytes from memory, we're doing bit twiddling to look at them and figure out what we're doing. We have some kind of a case statement implementation, and there are many ways of implementing that, but we still have to do that. And then after we've done that, then we take this jump. In this case, we just go jump, 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 jump. We're not doing any of the bytecode stuff at all. In fact, you can throw the bytecodes away if you don't have to reflect on them because your language doesn't require it. You can stick with just the threaded addresses once you've generated them, if that suits. So that's one big source of speed up. You know, this stuff in this loop. Okay, so we push the unpredictability of this branch sort of out to here. But with the calls now, we've made the branches and the returns much more likely to be predictable. So, you know, if you have the time and the interest, go implement some of this and measure it, or just build a little example and measure and see how much difference it makes on a particular architecture. But I think you'll be surprised at how significant it can be. And you have to set up a realistic test because, like I say, if I don't put any instructions here, if this is just ret, there's no architecture in the world with any depth of pipeline will be able to predict this in time to avoid a pipeline stall. But if you actually do some work in there of significance, then you can make it go.
So at the high level, the reason that we can do this is because we've structured it ahead of time, and then it just follows the structure.
Yeah. We've basically
dynamically executing the structure.
Yeah,
which means that you can't do it.
We've done the decode of the bytecodes once and replaced them with a much more machine-friendly representation. And if you go to the calls, we've basically transformed from a loop interpreting bytes in data memory into direct execution, calling the individual action routines. And we haven't done anything to the action routines, right, at all, other than deal with a return sequence to make the threading work. You can actually express this in GCC. GCC has this facility, which maybe you saw in one of the papers I sent, which is that you can have labels and use them as targets of computed go-to. So there's an extension to C in GCC.
But it's a go-to, it's not called.
Yeah, that's right. It's a go-to. That's right. So you can do that one with a loop. That one with a loop by replacing this with C code that's doing go-to through branches. You can't do the. I don't think you can do the calling version, as you say.
Mario.
an interesting note about that is in the paper they talk about using the computed go-tos as sort of a clever use of this feature. And they just, GCC had this feature and we saw that we might be able to use it for this. If you go now and you look at the GCC documentation, the documentation explicitly says threaded code as the motivation for computed
Yeah,
go-tos.
why would you want computed go-tos otherwise? Like, it's just like,
So it's sort of like
it's how to obfuscate
they sort of
your
flip
program.
roles after a while,
Okay.
Well, interpreters aren't the only use of switch dispatches. And if you just use a normal switch statement,
Yeah, it's
you're stuck
yeah, right,
with this indirection.
right. But it's not. Most programs don't require, aren't that performance sensitive on the individual switch statements. Okay, so to generate the threaded code, we're going to run an abstract interpretation over the bytecode, and then that'll emit the addresses of the action routines. And you've seen abstract interpretation before. And as I said, at that point, if our language doesn't require, or our environment doesn't require access to that bytecode, we can throw it away because we have an equivalent representation there that's executable. If you have a language in which you can, say, reflect on the bytecode, or you can change code dynamically at runtime, or whatever, you might, that will constrain your freedoms in what you do here. The other technique, if you're not able to throw the bytecode away, is you can throw the generated code away, right, and just regenerate it, because the generation routine here is really fast, right? It's one abstract interpretation, which is going to be certainly no slower than a full interpretation of the code, unless the individual bytecodes are doing more or less nothing. So you should be able to generate code really, really quickly here, which means if you run out of space, you can always throw some away and regenerate it when you need it. Okay, so in the original paper, as I said, it was going to be used by a compiler, and it would have these fixed routines to do things like adds off in a library, but it would generate the code to do the tailored things, because if you think about it, if you bytecode, suppose you have a bytecode set which has push local variable onto the stack. Well, there's going to be push local variable 0, push local variable 1, push local variable 2, and some flavor that goes up to some fairly high number. Well, in this scheme, we have no decoding capability now, so you'd have to have all of them there all the time, right? Which is fine if there's only 256. If the 64K possible variants, then things are beginning to get a little painful now. So in the original scheme, they weren't doing that at all. They were just generating the simple action routines on demand based on the indices that they knew the program had to begin with. So the question then arises, well, suppose you have the same constraint, as I mentioned earlier, that you want to have a read-only binary. You're not able to generate and execute code. Can you use this? Is this even feasible? Well, there's a number of sort of escape acts you can pull off to go down that path. How do you deal with the fact that you'd have to have a massive explosion of cases? So one of them is the hint, at least, for how to do this comes from a paper only a couple of years after the first one called Indirect Threaded Code. And the trick here is like all computer science tricks, which is you add a indirection. So instead of having a pointer directly to the action routine, we have a pointer to a little chunk of memory. And the chunk of memory contains a pointer to a getter and a setter, and the value of the variable that it's getting and setting. And now, instead of jumping here, we jump through here to here. And we can share these things depending on what our program is trying to do. So this example is doing b equals b plus c. So it points to the getter for b, it points to the getter for c, it points to the adder, and then it points to the setter for b. One way of thinking about this is you can think of these as objects, right? This is the mean for an object. Data and code, pointers to the code for the routines for the object. And that bear that in mind, that'll solve an additional problem. So this is the sort of schematic of how this would work. You have now your code is pointers to the appropriate getters and setters, but not directly, indirectly through through these data objects. So for each variable, you need a separate couple of words, one pointing to the getter and one pointing to the setter, because these are, this is, I'm assuming, a stack machine. There's just a pair for each. And these then point off to the routines that are shared by all of the variables in the system. And the ones that don't need any data, that just have the interaction point to the appropriate action routine. So now the threading says, grab the pointer, load that, go to the target. This is the code here. Load that and call the thing that's pointing to. So it's a little. This is now this thread is now a little slower because we have an extra load in there. On some machines, this is still one instruction. Just depends on your addressing those. Now there is a problem with this. It's fine for Fortran of 1975, because for the Fortran of 1975, it had only two things more or less. It had statically allocated variables, and it had arrays, and that was really it, right? There wasn't a stack because you couldn't call it, recursion wasn't allowed. Every function could have its variables allocated at fixed addresses known at compile time. And so this is great because because you can just make each of those locations, instead of being one word, 3 words with the getters and the setters, and who cares about an extra 2 words for every variable in your program? Variables just are not that common, right? Code is much more bulky than variables. And for the arrays, you just need a getter and a setter which takes an index as a parameter. So you're passing indices through some convention. But if you think about doing this for a language with a function stack, for example, or a method stack, it suddenly gets a lot less appealing, because now when we create a stack frame, for every data slot in the stack frame, next to it we have to put a pointer to a getter and a pointer to a setter. We have to fill that in when we call the function, which is not so appealing. So the trick to get out of that is, use this observation that I mentioned earlier, which is, think of these things as objects, right? We already showed how to abstract behavior out using a map, put a pointer into something else, and we can make these be anything we like when we're doing the implementation, right? So this could be a stack frame, as long as we can somehow pass an index to say which slot of the stack frame we've got. And now we're only putting 2 pointers in per stack frame rather than 2 pointers per variable, which is much more attractive. So at that point, really, you end up with, you have to change your instruction set. But remember, this is a generated instruction set. It's not the original bytecode. We can decompose what we execute into smaller pieces if we want. So for example, instead of having a branch to offset n bytecode, which means we'd have to have n action routines depending on the field width of that operand, we can just push n onto the expression stack and use that as the parameter to a single branch bytecode that takes that from the expression stack. Now, as we add more indirections and more of this stuff, we're sort of going farther away from the original high-speed implementation. So now this is where things get sort of very sensitive to the specific implementation and the specific architecture and the specific organizations. It's harder in a scheme of this complexity to say, this will be a win, right? You might, through all of this extra stuff you have to do, you might lose what you gained earlier. So that's why this, I don't think I've ever seen an actual indirect threaded implementation. They're pretty obscure these days. So this is what the bytecode would look like. Instead of push local 3, we'd have push a 3 and then get the local whose index is on the stick. But we do end up with a system in which the only mutable state is in data memory. The code itself can be in a fixed, built ahead of time binary, even in a ROM, which might be important. So threaded code, even though it dates back to the mid-70s, it really gained in popularity with its adoption by Forth, which I think dates from 78. How many people are familiar with Forth here? Okay, sprinkling. It was once upon a time where like everyone in the room would have raised their hand because it was extremely popular in the 80s. It was developed by an astronomer for a way of controlling his radio telescope, writing programs that would be easily modified and yet run with a reasonable performance, for which the compiler was more or less trivial. And it caught on really well in the 80s. And then the technique was adopted by Adobe in the PostScript language, which is what's inside every PDF. So every time you render a PDF, you're more likely than not running a threaded code interpreter. In fact, if you're using the GoScript implementation, using Peter Deutsch's threaded interpreter, you can see it just a few weeks ago. If you haven't seen PostScript, it's kind of fun. It's a little wacky, mind-bending. So once upon a time, before things like printer drivers were common, we used to handwrite this stuff to make diagrams. So this is actually code lifted out from a PostScript file of mine from the 80s, which is part of a diagram for a paper. This is how you drew a diagram in a paper that you were going to laser print. You wrote a program to render the diagram by hand in PostScript. And so this is, the things with the slashes are symbols, so they're just pushed onto the stack as pointers to the underlying atom that contains the string, and then it's a left to right, RPN type evaluation. So this, if you call call size, this is a definition of a function, right? Def defines that guy. The percents are comments. So it has to be heavily commented, right? Because if you don't write comments, you can't figure out what the hell it's doing, even 10 minutes later. So this is taking 4 and 5/30 seconds and multiplying them by 72, which is the unit of coordinate system in PostScript. Points. 72 points per inch. So that's how I get 4 and 5/30 seconds of an inch. That gives me an inch, and then this is a longish method, and after every line I write a description of what that line's going to do to the stack. There's a comment to figure out what's going on. And it's, there's divides and multiplies and variable fetches, and then calls into the graphic system like move to, which is moving the drawing point in the coordinate system. And it's kind of fun. When I was a grad student, the fastest machine we had was a laser printer. The processor in an Apple LaserWriter was faster than anything else we had on our desk. So some people actually ran the programs in the printers. I had a friend who wrote a theorem prover that ran in the printer and then printed out his answer. But it is it's a little sort of mind warping to write lots of this, but it's very immediate, especially if you're talking to the command line and the interpreter. Okay, so that was one technique. Let's move on to the next. So the next one is called stack caching, and the idea here is to try and exploit a phenomenon, which is that in a byte-coded stack machine, most bytecodes are doing something to the top of the stack. Right? You're either getting it, or you're writing it, or you're doing an add with it, or you're putting something back, or whatever. And that means if you implement it in the way you guys have probably done it, that the top of stack is a location in memory indexed by a variable, you're offsetting to an array, which means you're doing a load and a store every time you access that thing. Well, one of the tricks you can do instead is to say, aha, the top of stack is not going to live where it should. It's going to actually live in a register. And the rest of the stack will live where it should. And then you rewrite all of your code with that assumption. So you rewrite your bytecodes to use that register directly. So an add, instead of doing a pop and a pop, and then an addition and a push, grabs the register and does a pop, and then an addition puts the value back in the register, because it's going register to register now, the top of stack. And again, there's another one of these things which is darn difficult to express in a high-level language, so you tend to have to write assembly or generate assembly. Now, there are a number of variants of this which will come in. One is that most hardware partitions its register set so that there isn't a single good place to keep the top of stack. because if the top of stack is an integer, it wants to be in an integer register. If it's a floating point number, it probably wants to be in a floating point register. On some machines, you might even have separate registers for addressing and memory operations. And then, like, well, where do we put it? There's really no good place. What you can do then is you can put it where it sort of wants to be and track that state in the code. Now, the easy way of doing this is by having some state variable, but then you have to test and set the state variable, and that's wasting time. A different way to do it is to actually change the dispatch table to reflect which state you're in. So you know, if you can't infer the state from the bytecode, which in most bytecodes you can't, even in Java you can't, you go down this other route, which is to have multiple dispatch tables. So again, you currently probably do your dispatching through a switch statement, but in assembler what you probably do is have a vector of addresses for your dispatch, or threaded code that's doing the dispatch. Suppose you have the vector of addresses, which is indexed by bytecode, pointing off to the action routines. Well, you can have multiple ones of those laid out such that there's an index pointing to which is the current bytecode dispatch table. And you change that according to the type of the thing that's the top of the stack. So suppose you have two dupe bytecodes in a Java file. One is known to dupe an int, and the other one's duping a float. How do you know that? Well, that's because the thing that preceded the first dupe, must have pushed an int onto the top of the stack. The thing that preceded the second dupe must have pushed a float onto the top of the stack. Well, when each of those executes, it can set up the dispatch table. The first one would point to the dispatch table that assumes the top of stack is in the int register. The second would point to the dispatch table that assumes the top of stack is in the float register. Diagrammatically, it's like this. So these are the dispatch tables. So if it's bytecode, there'd be 256 entries. Each of the entries would be a pointer to some code that's executing the appropriate action for that bytecode. So this is, say, the int table, that's the FP table. If we look at, say, the add column, which is this one here, there'd be an I add here and an F add. Sorry, mistake, ignore that. If we look at, say, the dupe column, there would be a dupe bytecodes in each of these, but the behaviors are different because we know ahead of time that this guy is going to dupe an int and this guy is going to dupe a floating point number. So what we do is, in the iLoad code, suppose we're currently in the case where we're in the int top of stack. When that guy is executed, it's going to assume the current top of stack is an int, so it has to push that aside onto the stack. And it's going to load the variable, put it in the int top of stack. But there's no state change because we didn't change behavior. If we were in the FP state, then that would have to spill wherever it keeps the floating point top of stack to the stack. It would load the value of the variable into the int top of stack, and it would change this pointer now to point to this table. And next time we would dispatch through the other table, and the dupe bytecode would assume that the top of stack was in the right place, namely the int top of stack register. I'm not sure I did a good job of explaining that. Do you get it? Yeah?
But so it requires this pre-analysis to convert all your dupes into either.
No, not necessarily. That helps, but you don't have to. Because in this particular case, your dupe bytecode is the same bytecode, so it's indexing into here. It's just going to pick up the right one. The pre-analysis only helps if you can't, if they don't line up nicely. So we've got two behaviors for iLoad 0 for the two different cases. We've got two behaviors for dupe. Why isn't there a second behavior for add in the floating point vector? Why do I not have a pointer in that box?
Because your bytecode is typed.
Yeah, we know by the properties of the bytecode we can't possibly be there executing an I-add with a floating point number on the top of the stack.
So if you look at something like Java bytecode, how many extra opcodes are you creating? right?
Well, you're basically taking all of the typed, you're multiplying by how many different caching variants you have. I mean, you have to fill out the matrix for all of the legal possibilities. Like, this isn't a legal possibility, but most of the possibilities are legal. You know, the preponderance are. And these are all now going to be specialized based on that behavior. Many of which are going to just be, you know, I've got the wrong thing, I'm going to switch to another state, I'm going to spill something to this stack, do what I would have done, and then push the new thing into the new location.
So that's gonna increase your
Code
instruction cache.
Oh yeah,
Or it's
absolutely.
gonna really increase your microcache.
Yeah, but caches are big.
x86 gets translated into essentially RISC-like operations.
You mean like a trace cache or something like that?
Trace cache is one thing, but the microcache is 1,536 words broken up into six.
Yeah, you'll probably blow that out. But I can't imagine a Java interpreter would run in that amount of space anyway. You know, so it's not clear it would get a lot worse.
Yep. So if you assume something like bytecode verification has happened ahead of time, and if I'm not mistaken, and you can even figure out when the dupe instruction is seen in, let's say, a JVM bytecode, then it's going to be duplicating an integer or float because you've got the control through the handler.
Right.
Then couldn't you, instead of having just one entry for the dupe bytecode, like your bytecode might be compressed because you want small code sizes, but then
Right.
when you're translating
If you can expand it,
yes,
if you
make
can
a larger
expand
one.
the byte into, you know,
Along
the problem is if the thing is already filled, if it's packed,
Yeah.
then there's nothing you can do. If you have spare entries here, and actually there are some spare slots in the Java bytecode set, you could reuse some of them by rewriting an int, you know, a generic dupe into the typed dupe flavor, if you really wanted to. But the nice thing here is you can make this one point to an error. And that means that you sort of get an extra level of redundancy behind your verifier. That means that, you know, even if something got through the verifier, it would not attempt to do a floating point add on an int. Or vice versa. Okay, so that's trick number 2. The generic set of tricks number 3 is make in each bytecode do more. So another way to reduce that overhead is to have more work in between the parts that are overhead. So you sort of fatten up the bytecodes to do more work. And in some bytecode sets, there are already instructions that do a lot of work. If you look at Smalltalk 80, for example, many of the bytecodes are like Java bytecodes. They're just stack manipulation. There's nothing much there. But there's this one, actually a small family of graphics bytecodes, with the underlying one being BitBlade, which is bit boundary block transfer, came from the Xerox Alto many years ago. And that basically takes some rectangular chunk of a bitmap and copies and blends it with some other rectangular chunk of a bitmap into a destination. And you know, that's how the screen is filled, right? So one instruction fills the screen with gray. So, you know, that instruction, the interpretation overhead really isn't important, because that thing's going to touch, you know, a megapixel or more.
Isn't an extreme form of this just turning your entire program into a single bytecode instruction?
Yeah. But you have to then generate a VM that will execute that one bytecode. You know, you need a different VM for every program then, which is...
I mean, you generate assembly then, right, from your directly.
That's a binder.
You call it a compiler, yeah. Your program becomes... Traditionally, there's actually 2 instructions. They're called solve problem, print answer. It's almost a risk. Now there are these things that already do a lot of work. Another example, a better example actually, is R, and especially its predecessor S, which was designed more than 20 years ago. The idea there was that the statistical language would basically just be a glue that would wrap around a bunch of stats operations on vectors and matrices that were written in Fortran and C and C++, and all the performance was in those things. So the glue, kind of, who cared what the interpretation overhead was if an individual bytecode was, you know, calculate some statistical property of a megabyte of data. Alas, things have not really worked out like that over the years. But so the performance of the interpreter actually is much more important, because surprisingly enough, people would rather write R code than Fortran. What a shock. Now, there's a way of actually doing this semi or even fully automatically. The technique given to the name is called super instructions. So the idea here is to synthesize bigger, fatter instructions from common sequences of smaller ones. And you start typically by getting some big corpus of bytecode programs and you're running an analysis over them, looking for common pairs and triples and those things. Obviously, I have to be entirely contained within a basic block because you're not going to be able to jump into the middle or out of the middle of a super bytecode. So you look for these pairs and triples and quadruples and however many, however long sequences you are, and you statistically analyze which are the most common sets. And then you can either by hand go in and modify the bytecode compiler and the interpreter to emit and execute those things, if that's a possibility, or you could take a single pass over the original bytecode, sort of jamming the patterns together just before you execute them for the first time. Either way works. It's kind of tedious to do this by hand. So an example might be push local, inc pop local. Right? That's probably a very common sequence in any bytecode set of any language. Increment a variable. Well, you could replace that by a single new instruction called inc local that does all three all in one go, and you could encode that in, match on those sequences, and emit that thing. And it's kind of the opposite of the risk movement, right? You're trying to make the instruction set fatter and heavier because the dispatch cost, the decode cost is more or less constant, even as you go from hundreds to thousands of instructions. It's not really a big deal in software, but you get more work done in each of the opcodes. There was a whole bunch of papers written on this around the early 2000s. In fact, there was a big sort of wave of interpreter tweaking and improvement from the mid-90s through the mid-2000s, mostly done by a pair of guys in Europe, Anton Ertl and David Gregg, who co-wrote papers. So you'll see Ertl and Gregg as a common pair, and they did a big thorough analysis of what this technique and all the other techniques, and figured out, at least for the languages and the implementations that they had, what worked and what percentage, and how to get tenure and all that stuff. So the next one is like kind of a combination of that and threaded code. And this is called, rather blandly, selective inlining. This was actually, it was first described in a paper by a former student of mine, actually, Ian Pimata, and his colleague then, Fabio Riccardi, in 1998. It was independently invented by the initial hotspot team and implemented in the very first hotspot system. And there they called it snippets, which also isn't a great name because it sort of means many things to many people now. The term has been reused in many places. So there isn't really a great name for this, but the canonical paper is this one on selective inlining. And the idea here is it's sort of like threaded code, except instead of replacing one bytecode with one pointer to an action routine, we're going to replace multiple bytecodes with one pointer to the action routines all concatenated together in memory, and thereby save on the threading between them. The best example of this was actually in the original paper. So over here we have C code for a little table that's pointing to 3 opcodes, push 3, push 4, and add. So this is doing the 3 plus 4. And you can see the C code of the interpreter, which is the usual kind of thing, a switch statement, a little bit of code for the action routine, and then some macro that's going to go on to the next one. And what the rewriting system logically does is it transforms this into this, takes the action bodies out, jams them all together, and then does the normal dispatch at the end of that routine. And it has to rewrite the threaded dispatch to skip over the ones that are no longer there as individual instructions anymore. Because now you've replaced 3 instructions in the original sequence with 1 in the final sequence. There are some restrictions on this. Firstly, if you're going to be doing this jamming together and concatenation, obviously the code you're copying to do the concatenation has to be relocatable, otherwise it's not going to work. It can't contain relative branches outside the sequence, because they're not going to work either. The control flow changes can only happen in the last one, so if there's a goto, it can't be the middle. It's kind of pointless to have it in the middle one of a sequence. And the branch targets have to still be viable branch targets at the heads of sequences. So one simple way of restricting this is only translate basic blocks at a time using this. But you can, if you get lucky, you get one basic block is translated into one instruction with the code associated with that action. And because it's such a fast technique, you're just generating threaded pointers and concatenating regions of memory, you can throw away the code fairly lightly, because it didn't take a lot of time to generate. So you can turn over the code very quickly if you really want to. You don't have to amortize the effort of generating it over many, many executions. So in their implementation, and also the hotspot one, they cached and reused the generated macro opcodes. So what you want to do is, once you've generated one of these sequences, if you can find the same sequence again, you can reuse it as long as you're careful. Now, all of these techniques, as I said, are pretty much impossible in a high-level language, even in C, which is barely a high-level language, because you have to control so many levels. So if you look at the way things have been done in the past, typically the approach is either to write a generator in a high-level language that sort of builds the interpreter and emits it as a glob of machine code, or you invent your own DSL in which you can capture all of these things, and then of course then you still have to write a generator for your DSL, but presumably it's not quite, maybe not so quite as contorted as it was in the first place. And there's a really nice one that came out in 2002 again from the Ertl and Greg crew called VMGen, in which they sort of invent their own DSL, and they build a big system in which you can express, I think, all of these optimizations, and it spits out a piece of code that will do your interpretation. The other approach of having a generator is the one that's used in Hotspot. For those of you who've looked at Hotspot, there's kind of both flavors, the generated and there's the static. But the generated one is like the version, the static one is this. Sweep it under the carpet thing. I don't think it's maintained or supported or anything like that yet. But the generator one has been there since the early days, and it does a lot of this stuff. It uses stack caching. It has different states for the various different JVM types that can be in the top of stack, and it has dispatch tables per all of those. It's written in C++ with templates, so it's kind of, there's an adventure in doing this in C++. And then it doesn't directly compile the C++ into the interpreter. When you build the VM, when the system boots, an internal generator sort of reads these descriptions from the C++ code and emits the associated action routines. So the C++ is kind of thinly disguised assembly language. And it can do clever things like, if you find you're on a Pentium 6.3 or whatever the flavor is with a foobar instruction, well, now you can use the foobar instruction if you really want to, because you know which machine you're on. Whereas, if you write one and you just distribute a binary ahead of time, you have to use, typically you're sort of in the lowest common denominator model. So it does that too. It used to do the selective inlining trick. They took it out. I'm not entirely clear as to why they took it out, but we can table that question for when Lars is around in a few weeks. Okay, so final word before we take a break is, all this stuff will definitely speed up your interpreter, and there are, a small number of other, I think, marginal techniques which are in the literature too, which are worth knowing about if you really, really want to squeeze out the last ounce of speed. But, I don't think any of this will get you even remotely close to where a decent compiler will get you. You can get fairly close to a simple JIT, fairly close, but you'll never get to anything that does any decent level of optimization. So after the break, we'll make a start on compilation, which will take several weeks probably. Okay, any last questions before the break?
One of Anton's papers made this claim that difference between these threaded interpreters and a naive JIT that just copies segments is all controlling the branch predictor. Would you agree with that?
Yes and no. It might be true on some specific microarchitecture. If you can play games and match the branch predictor carefully, yeah, you can get performance of a really good interpreter that approaches a really bad JIT. But it's really hard when each has equal effort put in to make them live at parity. That's my take on it. I mean, there are all sorts of bizarre things you can do. One of the things we did, so I worked on the pre-hotspot Sun JVM that was shipped on Spark and Solaris, which was a code base written in C. The interpreter there was handwritten in assembler, and it was carefully written such that the branches or the action routines laid out in the iCache so that there were no bad iCache conflicts, right? Because you can put them at any address, right? There's just a table pointing to them, so you can rearrange them everywhere. Everyone was aligned on the appropriate binary for the beginning of a cache line, and the analysis was done to say, oh, these two are common, pairs, but they'll land on the same cache line. Let's move this one to a different address. So you can do a lot of work to try and but that's specific to one specific chip. And that's not going to. That stuff isn't going to work on the thing that follows it or the thing that precedes it. It's a lot of work per thing, whereas a compiler is just like this big hammer.
The compiler's not going to do that.
No, but it doesn't need to. It doesn't need to. Right? It's going to be several times faster without breaking a sweat, probably. So that level of fine tweaking just isn't necessary.
So, in the context of interpreters, there was one technique that I was hoping to see. And I know it's from the company that I shouldn't mention that stole some stuff from you guys. Dalvik kind of generalizes registers, and all of these interpreters, all of these bytecodes were kind of like invented.
Stack machines. So it uses a register
in the 90s when when there weren't very many registers.
I would argue that
nowadays
there were plenty of registers on Spark.
Okay.
When Java was invented, the reason stack machines are adopted is because it's neutral.
But
it doesn't.
That's why they were adopted. But why do we retain them?
Because once you compile, it doesn't make any difference. It's as good an IR as any other, really. So going through all the bother of trying to do register allocation in the distribution format, only to have to do it again when you find out the real machine and how many registers it's really got. Why bother?
Register allocation isn't free, and you're doing it at runtime.
Yeah, but you have to do it at runtime anyway, because only at runtime do you know what you're on. Right? If you're not distributing a binary, you're only going to discover the underlying architecture at the point where you start executing it, and you have to make your decisions at that point. You could argue, and there were some studies done that said, okay, let's devise an IR that's an infinite register thing, and we'll prioritize them. So the thing we want most to be in the register will be in register 0, then the next will be in 1, and the next in 2. And then when we generate machine code, most of the work is done for us. We just take the first n and put those in registers. I mean, a little difference, but not much. Not much. Not when you compile. Because there are all these other issues that you have to deal with when you're compiling. And that's like...
I guess I just have a really low opinion of compilers.
Okay, well, we'll change that.
If you looked at LLVM or if you looked at GCC.
Okay, let's take 10 minutes. Okay.
They argue that they're latency. Have lower latency.
It's kind of amazing that it took half the course to get to this point. Because when I envisaged this course, I thought, I'll be there in week 2. All right, So, some mother had an apple pie. We need to get past interpretation, right? If we're going to get more performance, you can whittle away these few percent through all these techniques. But as you saw from the interpretation techniques, you get more and more machine-specific and microarchitecture-specific, and you lose some of the advantages of portability and things. So if we're going to get performance, you have to break out of this one at a time mentality and go into compilation and compile a whole bunch of stuff at a time, and that will give you, once you've got your hands around more of the program, then you can figure out more what's going on and take advantage of the behaviors. You know, in special case, you know, compilation can be expensive, but the goal is to try and amortize the cost for the stuff that's being executed many times. It's generally not a good idea to compile stuff that's going to run once or a few times. It's very hard to build a compiler that will win in that situation, and compiling stuff that's never run is never a good idea. Okay, so why are we doing dynamic compilation? Hopefully this is all fairly obvious. You know, the world seems dominated by static compilation and binaries, and these reasons should all, I hope, be obvious. You know, binaries are not portable, hard to verify for security properties. For some languages, you might not know enough ahead of time to be able to generate good code because of the way the language is designed. You know, they're big. You end up compiling everything, even though a lot of it might never be executed. And the encodings, you know, are often not compact compared to bytecode, although there's always GZIP. Some other advantages, a little more elusive, but nonetheless real. One is that, you know, when you're compiling, your program is now running, right? You can look at the actual data that are being manipulated, and you have, you know, the pieces of the program. If it's you know, like Java with class loaders and dynamically assembled from disparate sources, well, the only time you get to see all of the pieces together is at that point when the program is actually running. In fact, sometimes not until the program's been running quite a long time. And you also know things like, you know, the specific model of the CPU you're on. So you can select model-specific instructions, as I mentioned earlier. You know the size of the memory you've got. You can know the structure of the memory hierarchy. You can do all sorts of tricks here. This seam has been relatively lightly mined from the point of view of dynamic compilation. Most of the low-hanging fruit has been elsewhere in just trying to figure out how to get good code on sort of the generic processor, and mining this kind of knowledge is still fairly open. So, you know, any of you have interest in this would be a good direction for some research. Especially in conjunction with people who are building machines. Okay, so we have a bunch of, actually there are many, many compiler design choices, and I'm certain I'm not going to enumerate the entire list, but I'm going to make a start on these, and we'll cover a few this time, and we'll see more later. But you know, one choice you have to make is what's the unit of compilation? What are you going to compile when you compile something? You're going to put your arms around some piece of code. How big is it? Well, you could start with a basic block, but generally speaking, they're too small. There just isn't enough there to do anything useful with them. You don't see enough going on to really get some good optimization opportunities. This is fine for, you know, the selective inlining technique that I described, or a very, very, very simple JIT, but beyond that, sort of, it just doesn't seem to be enough. So a method or a function or whatever, whatever your programming language naturally decomposes to is a better place to start. But of course, the variety of grain sizes there is immense, right? The smallest methods might be just like, you know, itself a variable, and they might be really big. So that still has some problem. The method of time compilation, you might not be seeing enough to do something much more interesting, and where we're going to get to hopefully next week is many methods, all related to each other via the call graph and potentially inlineable, because now you can really get your teeth into something worth compiling. A whole different branch, a whole different fork of compiler design is compiling traces of execution. So this is the idea that you watch as the program steps through a bunch of instructions, you know, and you gather that list of instructions, and it can span methods, it can span loops, it can do all sorts of interesting things. You gather that thing, and you do something to compile that trace, which originally will be something like a bytecode trace, into a machine code trace. Trace compilation is quite different in many ways from all of this. It has its own sort of literature and topics, and I'm planning to get a guest speaker in who's really expert about this in a few weeks. So I'm not going to say any more about trace compilation until then. We're going down the other path of compiling methods or groups of methods. So another important distinction, and probably the one which you're maybe more familiar with, because the previous one sort of people just take as granted that it's going to be a method often. But the more explicit choice which is presented is when. When do you compile? You can either, and I've broken into three, there's actually four here, I'll get to that. One is you compile ahead of time, and before your method executes, there is a long time. It can be any time between the program being written and the program being executed, and that typically where it's written is not the same place where it's executed. So it can be compiled by the developer at the developer side, which is the traditional static compilation model, but it can also be compiled ahead of time at the the application side or the customer side. So, for example, compiling at install time is an interesting choice. You can compile Java code at the point of which you finish loading a class, right? You haven't executed anything yet in that class. You just loaded it. You don't know what you're going to execute, but you can go ahead and compile it if you like. So that's sort of an interesting choice point there. There's also this second choice, just in time, right? And that to me has a very, very specific meaning, and I will describe that on the next slide. And it excludes these meanings. So the other, just in time, means compilation triggered by the first execution. So you get to some piece of code and you're just about to execute it, and you think, well, we know we're going to execute it now, so it's not a complete waste of time to compile it. It's not like compiling something that's never going to run, because you know you're going to run it at least once, and you compile it at that point. And of course, you have to wait for the compiler to end before you can execute the compiled code. The other end of the spectrum is to let it run once or many times and then do some compilation. And the advantage is there. Making things run once often clarifies a bunch of information that might be uncertain before the first run. So in Java, you've got this stuff going on called resolution, which if you try and compile a method that hasn't been through resolution yet, you're in a world of hurt, because you kind of come across a piece of code and you just have no idea what it's going to do, because you haven't resolved what it's referring to. So many compilers for Java wait until the resolution's been performed before doing a compilation. There are other languages that have similar things where the first execution tells you something that you couldn't have guessed before the first execution, but you don't have to wait for the second. And then you'll see, especially next week, that you can wait a long time, many executions, to gather information about the program behavior and then do a compilation. And of course, these are not exclusive, right? You can be doing compilation and recompilation over time, and we'll get onto the techniques for that as the section progresses. There is a fourth choice, which of course is never. Right? You can, and that's sometimes a good choice, right? If you know something's only going to be executed once, like a static initializer in a Java class file, probably not a good idea to compile that. Or sometimes you look at a piece of code and it's like, it's just too bad, it's too hairy, it's too big. Right? The thing about building a compiler in this environment, if you have an interpreter to fall back on, is that the compiler does not have to be complete. It doesn't have to be able to compile everything, because you can always punt to the interpreter if you really want to. Or if you have multiple compilers, you can, there has to be one level of execution that's complete, that does everything, but the others can just throw their hands up and go, it's too difficult, I give up. Okay, choice number 3 is the level of optimization. And the stuff we saw earlier was really, I think, interpretation, because we were doing the same thing for each bytecode that we would have done before. So minimal compilation is like macro expansion of bytecodes. If you do a little bit of people optimization, then you're doing compilation. And typically in a simple just-in-time compiler, you're doing something in this space. The register management is kind of done by hand. You pre-allocate which registers are going to be used for what purpose. You don't run a register allocator over the code later. You kind of have some convention as to where stuff lives. And you just follow that convention. Many things might still live on the stack and not in registers, but it's easy to write. It's fast to generate the code. And it's good at eliminating the interpreter overhead, which is the first limit. If you want to go beyond that, well then the list is very, very long, and we'll see some of the elements of the list in the coming weeks, but this is another fertile ground for thinking. Now this is my opportunity to rant. I have had this rant building in me for 20 years, which is that around the time that Java appeared, this term, just-in-time compilation, suddenly popped out of thin air. If I ever find the guy who invented this, I'm going to kill him. Because it's the worst term I've ever seen in that it's not only wrong, not only wrong in that it's actually not descriptive, it's that it's also universally misapplied where it shouldn't be. So it's not just-in-time compilation, right? If you look back at the term origin of just-in-time, it comes from the Japanese and manufacturing Toyota and that stuff. I have this book. This isn't just an image. And the idea in just-in-time manufacturing is at the point where you want to assemble the thing you're assembling, be it a car, all of the parts arrive just in time for that action. In just-in-time compilation, we don't compile just before the first execution. We don't know when that's going to happen and just arrange for the compiler to start its work so that it's ready. We start just too late, right? We're starting at the point where we know we missed the boat. So that's not a good use of the term. Also, you see this term absolutely universally misapplies to every form of dynamic compilation under the sun. And certainly, compiling 1,000 executions in is not just in time by anyone's definition. So I hate this term. I hate the use of the word JIT as a noun. If anyone uses that in anything they give me written, you will fail the course instantly. I have a concrete compromise suggestion, however, because I've been ranting on this for 20 years without much success. And here's the suggestion I have, which is to use the term JIT in lowercase now as a new noun, because it's English, we can invent nouns. So this is a new noun, it's lowercase, and it means dynamic compiler. Right? It has no relation to JIT in uppercase. And if you guys ever go into research and write papers, I hope you start using this. And if anyone pushes back on you from the referees, you say, justify the other use. Right? Explain why JIT, just in time, as a noun makes sense, or this particular term makes sense.
It looks a lot like Git.
So the appeal of the word as a noun is it's a single syllable, right? Instead of dynamic compiler, right? So one syllable rather than 6, which is great, and you can type it quick. But I capture that advantage. I embrace and extend this term.
So the alternative might have been lazy, and lazy doesn't sound very good either.
Lazy doesn't
It sounds
sound
kind of
good.
lazy.
Yeah, hard to go to your
Try to
manager and
write
say,
a
I want
work
to start a new
report.
project in laziness. Yeah. My research group used to be called a Kanban research group, and people thought it was because we did compilers. It's just that this is how we lived our lives, doing things at the last minute. More a life choice than a technical choice. Okay, so rant over. Thank you for listening. So the JIT compiler eliminates interpreter overhead. That's the big advantage. That's what Peter and Alan came up with, and why it's caught on in the last 20 years, nearly 30 years since then. Actually more than 30 years. So we decode bytecode only once, we generate code, there's no interpreter loop, and there's no other there's no thread to dispatch or any other form of dispatch, it's just code. So that's great. In a simple JIT compiler, the resulting code can be no more complex than just the interpreter actions glued together, as in that selective inlining case. But it's usually worth making at least one pass over that just to eliminate very simple peephole inefficiencies, simple constant folding tricks, just a bit beyond macro expansion. So why does this work? There's a very simple model which you can build. So this is a number of executions over time of a piece of code, and here's the time. And the idea is with interpretation, we're doing the same thing every time. So it's linear, right? One execution costs 1 unit, 2 executions cost 2 units, 3, modulo microarchitectural effects and caching and branch prediction and all that. But more or less, if you actually do this, you've got something that's pretty close to a straight line. It'll be noisy, but it won't, asymptotically go this way or up, right? It'll be more or less constant. The idea with compilation is we're going to invest some time in JIT compilation. We're going to invest some time up front to do some compilation, but the code we generate is going to be faster. So after some number of executions, we break even, and after that, we're ahead. So the important thing is, where is this point? How do we know where that's going to be? And we've got 3 parameters. The speed in which we can interpret, the cost of a compilation, and the speed of the compiled code. Now, in the real world, life is complex, and there are millions, of, well, that's an exaggeration, but many, confounding effects. But there's a nice, simple way of cutting through that and abstracting over it, which is we're going to think of the average bytecode and think of everything in terms of that. So the way you do it in practice is you find some benchmark suite that you think is important. So if you're an academic, you find whatever it is that's out there that's widely accepted for publication. If you're a commercial company, you find whoever it is, which benchmark suite is considered good marketing. If you're an actual user, you run programs that you care about. And then you measure the performance across this benchmark suite, subtract. Now it starts getting to be hard work. You have to subtract out all the stuff that isn't execution, like gsync and native code and other stuff that might be going in the runtime. But it is possible to do this. And you end up with the time it took to execute the bytecodes. And you simply divide that by the number of bytecodes that were executed. You put a counter into your thing to count the path length. If you have threads, you have to do a little bit more sophistication to deal with the threading. But you can measure what is the average bytecode over millions or billions of them. And rather than counting time directly, a common thing to do is to just count clock cycles. That really dates from the time when clock speeds were changing quickly. And so, if I reported time this year, next year it would be half the time, and the time year after that it might be a quarter of the time. Now, it's not really so important to do this, but you'll find papers in which stuff gets normalized to clock cycles. So I'm going to continue that tradition. So we have 3 metrics, which the 3 I mentioned earlier. The time it takes to interpret a bytecode, measured in cycles. Time it takes to compile a bytecode, time it takes to execute the compiled code for that bytecode. Okay, and then you can boil that down from 3 to 2 by taking just ratios. So in this case I have TOR, which you can think of as translation time. So the time it takes to compile the bytecode relative to the time it took to interpret it. And execute, which is the time it took to interpret it relative to the time it takes to execute the compiled code. And both of these numbers, ratios are chosen so that they should both be more than 1. So if you get out the back of an envelope and do a little arithmetic, you end up with this formula which says the break-even number of bytecodes is compile time over the difference between the 2 executions, or in terms of the ratios looks like this. And Here's an example. Suppose it takes 1 clock to execute the bytecode compiled, 2 clocks to execute it interpreted, and 10 to compile it. Then tau is 5, because 10 over 2 is 5, rho is 2, 2 over 1, and the base of the break-even point is 10. So we need to execute, in this case, 10 times before we're at break-even. Now that maybe doesn't speak to how the curve looks, so I plotted the curve, which will give you some idea of the range. And this is kind of covers the typical space of implementations. So on this graph I've got I'm plotting the logarithm of the break-even point on the y-axis versus the compiler speedup over interpretation, right? Or it's inverse, right? It's interpreted over compiled, relative for different curves for the translation time. So, if you could write a compiler that compiled in the same time it took to interpret once, then surprisingly, you get your investment back really quickly. But that's unrealistic. Toys 1 is you can just treat that as a bound, but it's not a realistic scenario. Even Toys 2 is probably not achievable in many systems, generally speaking. But as you can see, as the compile time goes up, the amortization time also goes up, and as the speed of the compiled code approaches the speed of the interpreter, the break-even point shoots up. So if your compiler is the same speed, the compiled code is the same speed as the interpreted code, well then you'll never get your compile time back. So there's this asymptote. So you want to stay out of this region. Your code has to be minimally, at least some faster than the interpreted code. And you want to try to avoid having really long compile times, because it's just going to be, you're going to end up spending time compiling stuff that it doesn't get you anything back. Yes?
Isn't this largely a function of granularity of what you compile? If you compile just one bytecode instruction versus 10 versus 20.
You mean the rate? Surprisingly not.
Meaning if I choose to compile 1 versus compile 10, I can do other optimizations like register allocation that's better if I compile several instructions at once.
Well, so the way to think about that in terms of this model is if you're doing more optimizations, you're moving up on one of these curves. So you typically think about having multiple curves depending on the level of optimization. That might even be embodied as multiple different compilers, right? Many of these systems have 2 or more compilers. So yeah, you would change as you're doing more optimization. But for something like a simple JIT, modulo the startup time to get the compiler going, the rate at which you compile bytecodes is almost independent of the number you compile or the complexity of the individual bytecode. Certainly averaged over a large set, and it's you can elaborate this model with all of those details if you really like, but this is just a good simple way to start thinking about things. So you can turn this round into a different picture, which is speed up. Okay, so if a bytecode is executed n times, then the speed up is given by these formulae. And now for any individual n, you can plot this curve, which gives you the speed up relative to n. So in this case, on a logarithmic scale, 1 is break even. So for these particular parameters, if I execute 125 times, this is a slowish compiler, Toys 100. If I execute 125 times, I'm at break even. It generates really good code, so it's 5 times faster than the interpreter. Asymptotically, it will reach 5. If I do less than 125, I'm wasting my time. I could have been doing something better. So this is the game. Yes.
Times is method calls, correct? So it doesn't tell me about how expensive.
Well, a loop. You can call the method once, but it can
Okay,
loop
so you are
internally.
Right.
Right.
So is it times method calls or?
Well, this is at the bytecode level.
At the bytecode level. Okay.
So if you call a method once, and it has a loop in it that runs 10,000 times, then the 10,000 is what you're compiling for. You sort of wasted your time doing the prologue and the epilogue, but if your compiler granularity is a single method, you have no choice. Okay, let's look at how we actually compile. We're going to have to do this. Remember this? This is our little bytecode interpreter for the expression language. Kind of the simplest thing. You know, what we've got is the loop and the switch and the actions and the management of the program counter. And what we're going to do here is basically factor out the parts that have to be done at runtime, but leave the rest of it more or less in place as it is. We're running, it's, for a simple JIT anyway, it's just an abstract interpretation over the bytecodes. And when we interpret a bytecode in this form, we just emit the machine instructions that are equivalent to the action routine. So let's go through some simple examples. Again, I'm using assembly code because it's just kind of more concise as a way of explaining it. So here's the interpreter code for that literal bytecode, which grabs 4 bytes from the instruction stream and pushes them onto the stack and increments the PC. Well, we're still grabbing our 4 bytes because that's a static program property, and we're still incrementing our PC, but in the middle we're going to do something different to emit the code for whatever would be left, which in this case is very simple. It's just the push part, right? And so you don't end up emitting code something like this. The simplest case is these first two. You're going to increment the stack pointer, which in a hand-managed situation, you know which register contains the stack pointer. You're going to grab the literal and store it into the top of stack. And you can either choose to put literals off to the side in some special area and grab it from there and manage that area and figure out what the index is of the literal in that area. Or you can construct it from pieces using whatever literal instructions are available in your instruction set. Or if it's small and it can be immediate, you just emit the code that emits that literal directly. And it's kind of the compiler's choice as to how you manage stuff and which of these you emit. You can get through. It'll certainly run fine with either one of these choices. This is like just an optimization. This sort of typical, simple, people style optimization that makes a real difference in performance, but that isn't very complex, and it's not going to result in you having to restructure your compiler to do something like this. Simple enough, yes? Okay, see some other examples. Add. Same thing, we're going to convert our interpreted pop, add, push into something that emits code that does that, but the part that manages the abstract interpretation is the same. So in this case, we grab a word from the top of stack, we bump the pointer down, grab the word next down, add the two together, and store. And in this case, one of the things you would do in your compiler is you assign certain registers for temporary working. And because you're only dealing with 2 or maybe 3 operands, you only need 2 or 3 of these. You don't need a full-blown register allocator because the real expression stack is on the stack still. We're not improving on that. And we can go on. These are all pretty simple. The get takes the address of the thing we're going to get, which in this particular language, remember the simple expression language where we just have 26 variables, we can compute the address of that up front and then just pass the address directly to the thing that emits the code. There's actually very little. All of these are structured in such a way that you're really just taking a piece of assembler, doing a tiny bit of tweaking to the assembler to fill in an address or something like that. It's very, very straightforward. It's not full-blown intermediate representation compilation. It's very, very simple. And this is all you need to do for the JIT for FEMA is this level of compilation. Put looks just like the get, except we've replaced the load with the store. The store rather to the location rather than the store to the stack. We have a few other things you might have to figure out. You want to be able to call into the runtime because you don't want to compile everything that's in the original program, probably. If you think about the implications of what's going on in your bytecode interpreter, you're not trying to eliminate, gut the whole internal structure and replace everything and everything it calls, because something like you're not going to inline your collector. Right? You don't want to write the assembly code for the collector and include it verbatim in the action routine of the allocator, right? You want to be able to branch out into the runtime whenever you get into a situation where the performance difference really isn't important. So, for example, if you're doing bump allocation, you try and make the fast path inline, so your allocator, compiler, when it sees an allocation point, emits the thing that tests for the pointer, not reaching the end of the space and doing the allocation. But if it does reach the end of the space, then jump back into the runtime and let your generic runtime handle that, because there's no point in trying to omit code for all of that stuff. You make only X a lot faster, if at all, and it'll be a whole lot of pain. Okay, so we also have to deal with managing our code, because we're in this situation now where you haven't been with the traditional static system, which is the management of code is the developer's problem, right? You just get a binary, the code arrives as a blob, and all you have to do is load it and link it, and away you go. Now stuff is being made at runtime, so we have to put it somewhere. We have to be able to find it again when we need to call it or link to it, dispatch to it, and optionally, we have to be able to throw it away if we run out of space, right? You can not throw things away, you can simply die if you run out of space if you want. But in a sort of a production system, you want to manage the space more carefully and throw stuff away, either if you run out of space or if the program, if that code becomes unreachable. For example, in Java, you can have a class unloaded after garbage collection. You don't want all the code from an unloaded class line around taking up memory space. So you want to be able to discard it too. So we need some kind of a structure to manage things in. You could just malloc stuff and throw it randomly in memory, but you'll soon find that becomes kind of painful.
So how big does this stuff typically get? It seems like it wouldn't be more than a few megs.
How big is your program?
Right, but programs don't get that big in absolute terms, right? I mean, it's hard to reason about 1 million lines of code, but 1 million lines of code is still like a few megs. Right?
There's, we have stuff at Oracle with 100,000 classes loaded from a single VM.
It still seems just like a few megs, right? It's not like gigabytes of memory.
It's not going to be gigabytes, no. It's going to be megabytes and not gigabytes, but it can be many megabytes.
Do garbage collection techniques apply here?
We'll get to that.
So, and the main gain that we're gaining is that, because let's face it, the compiler is also going to generate the exact same sequence as if I wrote those assembly instructions. The main gain is definitely that we're removing the branching.
Yeah, and any people optimizations that you can perform, and making things compact and directly executable. Yes.
So it's just the control flow that we're optimizing.
Yeah.
Right.
Yeah. I mean, you can, and we will look at systems that do much more than that. But I'm not going to ask you to write an optimizing compiler in the last 6 weeks. You'd be insane if you didn't walk out at the moment. Okay, so this function, that set of functions, is typically performed by something that's called a code cache. So it's a data structure in your VM that manages the code in your system. And so the way it's structured is the compiler that you write is going to emit the code into some kind of a large buffer. Because generally speaking, you don't know how big the code is going to be ahead of time. You can't size the amount of code until you've generated it, because you've got variable amounts per bytecode, and you might need extra stuff at the beginning and the end. So you have some single big largish buffer, which might be, I don't know, many kilobytes or a megabyte or something like that. Some reasonable amount for the biggest method you're willing to compile. And the compiler's going to emit code into this buffer. When it's done and you know the size, you're then going to copy that off into the code cache, find some place for it to live, copy it over there, link into it from whatever structures you need to link to dispatch into it, like the lookup tables if you're doing method lookup. And then you can reuse the buffer for the next compilation. So one of the things to observe is we're doing copying, right? Which means the code might run correctly in place in the buffer, but that's not where it's going to run. It has to be relocatable. It has to be prepared to live and run somewhere else. And unless you're willing to invest some extra complexity, you won't know that address until after you've compiled. So the best thing is to make your calls into the runtime, the parts outside of the code cache use absolute addresses so that the code can live everywhere but make everything else relocatable. Okay, so we're going to go into the structure and the techniques here in some detail, and I'm going to call the thing that gets emitted by the compiler an end method to distinguish it from the source level method or function or whatever is in your original language. So end method comes from the Deutsch Schiffmann N code, V code distinction, and in itself this was actually the C++ class in which these things were encapsulated, and the term seems to have stuck through a whole bunch of VMs now. So, so as I mentioned, in some languages GC can lead to your code being unreachable. For example, Java class unloading. It's good to free the end methods when that happens. Also, if your code cache is full, if you made it so that it has some fixed limit, or you let the user set the limit, then at some point you're going to reach, it's going to be no more room left. So you've got to flush existing things out of there to make room. And it's not just a question of freeing the memory and proceeding on. You have to delink the old code from wherever it was linked into the system, like in the method tables. Typically that will mean installing a new link to either trigger lookup or compilation, so that when you run that thing again, we threw away the code, but that doesn't mean you're not going to use it again. You're not going to attempt to use it again. When you try and attempt to use it, you have to either fall back to the interpreter or trigger the compiler again. You have to run stuff, so you have to prepare for that at the point where you throw the code away. But there's an even hairier problem, which is, suppose this thing is actually currently running. Right? We have a method which we're trying to throw away, but it's somewhere on the stack there's an activation record, and this thing is active. What do we do now? There's a few answers to this, few approaches. One, which seems, so first we have to find out whether that is the case. So how do we find out whether our method is active before we decide what we're going to do with it? An easy way is you can simply increment a count every time you enter a method to say it's active, and decrement every time you exit the method. You have to be a little bit careful here in that the exit, there are many ways of coming out with methods. There's usually only one way in, but there's often many ways out. And there's ways of terminating things that don't even involve the method, like terminating a thread or exceptions that cut the stack back or whatever, and you have to make sure you take account of all of those. But the price of this is that you're doing these increments and decrements. And as you'll see, you're probably going to have to build a stack scanner anyway if you're building a sophisticated system. So the alternative, this one, is the one that seems to be used most in practice, which is if you want to find out whether a method is active, you scan the stacks of all the threads looking for the activation records. So how do you do that? Well, the calling convention has to allow for the linear scan of the stack of a suspended thread. You don't want to try this on a running thread. That's really hard. You want the threads to be suspended, so passive in memory. Like if you have a single-threaded system, then the scanner is the thing that's running, and it can scan everything below the stack because it's not going to exit. So that's nice and easy. But if you have a multi-threaded system, you want all those other guys to be suspended. So you wherever they're suspended, you grab the registers. You have to find the registers, extract the stack pointer, frame pointer, whatever it is that's used in the calling convention, and then figure out how to walk down the chain of those things, looking at each frame. You have to find like if the return address is going to jump back into the method that you're trying to deallocate, because that's a good way of tracking whether that thing is active. Obviously, this is very, very highly machine dependent, and it's also very highly calling convention dependent. So if the stack only contains frames that are corresponding to the stuff that you did in your compiler, then you can arrange for this to be relatively straightforward. But if the system allows callouts to arbitrary code that can do sort of arbitrary things on the stack, that can make life very, very difficult. And there are ways to manage this. Next week, I'm sure Cliff will talk about this because this is a complex topic. But it is possible to do this, but it just makes life much more complicated. There is this worst case, unfortunately, where it just becomes impossible to do this. And I've actually seen this in practice. Under certain circumstances, certain OSs, under the right conditions, a page fault at the right moment during the thread switch, the registers are not in user space, they're in kernel space. And you can't get them. They just don't provide the system call to get them. All you can do is resume the thread. Right? So at that point, this technique is now impossible.
Could you send a signal to the thread and have it scan itself, basically, like an RPC?
Well, you'd have to get it to wake up to do that. You know, if the case where it's suspended in this particular example was something that was it was in the middle of an I/O call, and a page fault and an inopportune moment would mean that
You're trying to wait for all of that to finish.
yeah, well, right. So and it might not, right? Because if it's reading from the keyboard, right, what are you going to do? You know, zap the chair and say, "Type something, dummy." You know, it's not bounded, right? You can't force it to happen. You can abort it, and then you have to write compensating code that says, "Oh, did we abort from the system call?" And we have to figure out to be able to restart and resume. And yeah, it gets ugly.
Technically, you're supposed to do that.
Yeah.
What about just skipping that thread? Is it possible to just
Well, so the
make
danger
progress?
is that the thread contains the frame that you're trying to dispose of.
So,
If you don't know,
So
then, well, if you don't know, you can't dispose of anything. If you don't know what's on the thread, you can't dispose of any stack frames.
for that thread,
Right, but the thread could have any stack frame on. How do you know which stack frames, which methods are active in a
You
specific
have-
thread?
the thread's sharing.
Yeah, it's not nice. Luckily, this is fairly rare, although when you discover it in the middle of production, it's not nice. Okay, so suppose you've been able to successfully scan the stack, or you've used the counter or whatever to detect active end methods. Then you have the choice. Well, you can do two things. You can either say, I found it and it's active, and okay, let's not dispose of that one. Let's find another candidate to dispose of. We could just skip that one and try and make a hole somewhere else. That's okay. The alternative is you get into this other level of complexity, which we'll get into next week or the week after, which is you're going to fake as if it was never there to begin with. So you discard the method, you rewrite the activation so that when it's resumed, it either resumes in the interpreter or triggers another compilation to put you back where you were, and you have to recover all the state in the activation in just the right place and the right way, such that it looks like you were never in the compiled code to begin with. That technique is known as dynamic de-optimization. It's an extraordinarily powerful technique. It's very tricky to implement. There's a lot of subtlety in it. But once you've got that, it's an immensely powerful hammer. And you'll see in future weeks, once you've got this, what you can do with it, because it really is incredibly powerful. And one of the assigned readings will be the paper that described this for the first time. So we'll get to this, and you'll be looking at it some more. But it's kind of scary to go down this path for the first time. Yes?
Is that basically the opposite of on-stack replacement?
No, on-stack replacement is kind of a flavor of this. We'll get to that, but we don't have enough context yet to go into it. Okay. All right. So you've freed up the methods. Stuff is being compiled and allocated and freed and etc. But you're now going to face the same problem that you have in a heap system, which is you've got turnover in this cache, and you can lead to fragmentation. So when you come to compile a method, you find there's plenty of free space in your code cache, but you can't find a space big enough to put your code. This leads to another fork in the path, another design choice, which is do we compact the code cache or not? You can try and write a compactor. There's some extra complexity. You suspend all the threads. You shuffle all the end methods around to make the whole holds all joined together at one end. You update all the dispatch links so that everything's still self-consistent. You rewrite all the stack frames so the return addresses are correct. And you can make this work. The self-VM did this. It works. It's possible, right? It's not impossible, but it's complex. And there's another approach, which is let's just throw away some more code, right? We just keep throwing away code until we get a hole big enough and the thing is, you can be selective, right? If you have a backup execution mechanism, or it will trigger recompilation, you can say, well, this hole is not quite big enough. If I shot that guy next to it, then I'd have a hole big enough, and you can always throw code away in this kind of a scheme, because you can regenerate it later in some other place. Now, there's a performance cost to be had at that, but you're saving yourself the complexity, and that's the path that the hotspot VM went down. You know, same guy implementing in both. You know, Lars Back worked on self, and when he did hotspot, said, I don't want to do that again. But you can do it either way. This gets even worse if it's multi-threaded, so it's not been done many times. Another choice you have is, are you going to put the end methods in a separate managed area, or do you just put them in the heap with all the other stuff? The latter has some attractions. You already have a compactor and a collector, although they need to be extended with a lot of extra material if you're going to compact and collect methods, because you've got all this extra work to do when you move them. It's not just copying bits from here to there. You have to fix up things as you move them. So, but there is the attraction that you're managing all of the space in this uniform manner, so instead of having, you know, the other kind of fragmentation, which is tons of room in the heap but none in the code cache, or tons of room in the code cache and none in the heap. And when that happens, you know, you can't kind of start moving methods into the heap and objects into the code cache. So that's what you're hosed. So, this avoids that kind of fragmentation problem, but at the cost of some more complexity. So it gives you this unified heap management. You know, the downside, one of the downsides is that the most garbage collector systems are built with some assumption about the longevity and the demographics of the objects, and code tends to be very long-lived compared to other objects. And so, you know, if you have a system that's doing a lot of copying, you don't want to be copying your code around a lot and relocating it, because it's very expensive to do that. Another thing that might get you a little nervous is if you put the generated code in the heap, all you have to do is run off the end of that into the data part, or have the data run off the end into the code, and suddenly you have a really nice attack surface for someone to get into if you've got a bug in there. Whereas if they're very far apart, life is at least a little more difficult. So while we're talking about garbage collector, we have the other problem now, that we have stack frames associated with compiled code, and we have to find pointers to the objects represented by those stack frames as roots for our collector. And in fact, if you have a moving collector, then not only do you have to find the pointers, you have to fix them to point to the new locations that the objects have moved to, and you have to get this exactly right. Yeah, because you can't start wandering down the stack and rewriting arbitrary words to point to other things. Because the word you're rewriting might not be a reference, it might be, you know, a return address or a floating point number or something. So this makes for a challenge in precision in locating all of the pointers. So the pointers can be in registers, they can be in the stack locations for the end methods, and they can even, if your compiler was structured in that appropriate way, they can be embedded in the end methods as literals, right? You remember that example I had earlier where I was writing the spark to assemble a 32-bit object pointer in a register, right? You've got 13 bits of it are in one instruction, and the other parts in another instruction in some weird alignment. Yeah, and if that's an object reference, you have to find it and you have to rewrite it when that thing moves, which is another challenge. If that isn't bad enough already, worse, you can get into the situation where if your compiler has to do things like tagging or detagging, or it has to do some amount of address arithmetic to index a structure, suppose you suspend that compiled code in the middle of that sequence, halfway through one of these things. You end up with something that's, you know, half tagged or untagged, or pointing into the middle of an object rather than to the header. You can get into all sorts of complexities here. And how do we deal with that? Why is it easier if we have a non-moving collector? What problem does that solve?
You don't have to fix up pointers?
Yeah. If you have a non-moving collector, you're not rewriting any of the references, you just have to find them. So you could be a little bit in error on the conservative side. If you're in error and you find something and you mistakenly think it's a pointer and it isn't, that'll just mean that thing doesn't get garbage collected in quite as timely a way, but you're not going to break the program. Whereas in a moving collector, if you get one single rewrite wrong, the next GC, you'll probably discover that. Or before that, when that frame returns or something like that. Okay, so we have to locate the roots in all of these places, and so there are different techniques for this. One simplification is that, by definition, all the activations in the thread except the one on the top are at a call site. So that makes all but one of them degenerate into a simple case, which is how do you find roots in registers that are suspended at calls, in frames that are suspended at calls. So one technique for this is to emit a map, a simple bit map that basically describes which registers are live, and if the pointers can be untagged, this has to be a map of little live pointers. So you want the things that the collector has to find and rewrite mapped very precisely, and the compiler can emit this at each call site. For example, in the self-compiler, when it emits a call, it actually puts the register map in a word after the call, where you would think would be the return instruction, but it modifies the return convention to always return to an offset after where it would normally return. So the return is sort of bumps the pointer up a few to skip over the data that's associated with each call site. So so that's one trick. You just tuck them in the slots. Yes.
If you replay that trick, can you still use the processor reg instruction?
It depends on your processor. On Spark, I think you ret's like a general RISC thing, and you can give it an offset. One of the downsides there, though, we discovered is the hardware guys treated that as such a weird case, they don't predict it properly through the return address stack. So basically, all of those rets mispredict on a certain generation of Spark processors. C'est la vie. Okay, so that deals with the all but the top frame. The top frame, in theory, could be suspended anywhere, right? The scheduler can go, stop, I'm going to run somebody else. It can be any instruction boundary, if you're relying on the OS scheduler or and all of that stuff. So you could think about making a register map for every single instruction, but that's kind of prohibitive in space. Now you're building a lot of extra data to go along with your code. Maybe you don't care, to your point earlier, that the code isn't, what's 2x? If the code isn't big, what's 2x the code, right? Because it's only a word per instruction. But I don't think I know anyone's actually gone down that path. There are other approaches to this documented in the literature, some of which I think are just paper designs, some of which have actually been implemented. The most common one, which has been implemented many times, is to designate certain places as GC save points. And you make a register map for the save points in the instruction stream, and you ensure that when you do a stack scan, the thread is always suspended at a save point, and we'll get to how you accomplish that. Another idea is to keep the maps at various places in the code, and if you happen to stop in between two of those places, you pick the one previous to it, a dominator, in terms of the instruction flow, and then you abstractly interpret the machine code to figure out where the pointers could be from that point in the code. So, you interpret the adds and the loads and the subtracts and the stores and everything, and you figure out from that register map what the register map would be at that instruction. There's obviously a lot of complexity in that. You're basically building an interpreter for the underlying hardware in software, and you have to think very carefully about where these maps are known with certainty and where they can be derived with certainty, rather than, because if you're loading like from an element of an array, you don't know what's in that element but the type system might save you. So it's complex. You have to think very carefully to get that right. There are certainly published descriptions of this. I'm not sure anyone's really built this in production. And then another possible approach is just replay the compiler again But now say, oh, I need another register map of this instruction because I have a thread suspended there. And assuming you built your compiler in a deterministic manner, which is harder than you think, and it generates the exact same code it did last time, then at that point it will give you, the map at that point and you can use it. But in general, that's not used because it's just expensive to run the compiler, unless you have a very, very simple compiler that you're using for everything and you're doing no optimization. If you are, then that seems perfectly reasonable, and in those circumstances it probably is deterministic. Or close enough that you could make it. So, okay, so let's look at the GC save point trick. So the simplest approach, more or less, I don't know of anyone who's really studied this, in kind of a very careful, comparing all the techniques approach, but certainly this has been used in many systems, is to designate a safe point at the entry of every end method and at the backward branches in the end method. And the idea here is when the code runs, it will reach one of these points in some reasonably bounded amount of time. You can insert more of them to make it to decrease the latency of it reaching these points. So you could sprinkle them through a bit more. But this is sort of the minimal set run. This gives you the sense that every loop's going to stop at the tail of the loop, and every recursive thing's going to stop when the recursion is triggered. So that gives you some coverage, and then at that save point, you emit a little bit of extra code that tests a global flag that says, should I be suspending myself? Usually you just have to look at a single bit somewhere out in memory. And if so, then the thread, when it reaches that point, branches off to some other code that suspends itself. And if you like, it can even say, oh, am I suspending myself because we're doing a GC? Should I scan my stack and tell you all the routes, because you're already there in the thread and it's not going to return and undo the stack. So that's a good place to scan have the thread scan its own stack from that point downwards. So why, any thoughts as to why we do end method entry rather than return?
There's many returns, but only one entry.
Yeah, exactly. And there's code that has to be planted to do this. Now there's many different techniques for this that require more or less invasive surgery on threads, and we'll cover those in a future lecture. But this is good enough to begin with. Yes?
I'm a bit confused about the interplay between OS threads and your sort of VM concept of a thread, right? Because the OS has its idea of a thread, and it can interrupt you at any time for any reason.
Yeah.
That's the sort of abstraction
Green versus
of
native.
threads.
Yeah, so with this technique, it doesn't really matter how you do this, because what you do is at the point where you want something to suspend itself, if the OS has suspended it, you just
wait.
Either let it pick it up and run it, or force it to run by calling the appropriate thread resume thing.
Right. So
there should be a way of making it make forward progress, unless it's stalled in a system call or whatever, and that should be discoverable too by examining the stack. So there's a lot of complexity around the determination of the conditions here, but it's doable.
So pretty much so far when we're talking about looking at the stack and suspension and kind of all these sorts of thread associated terms, we're talking about the virtual machine's concept of a thread, and the OS concepts of a thread are sort of like we're sticking with the POSIX p-thread abstraction of it's always
it can be
running.
either. The two common situations are either the VM manages its own threads and it runs on only one OS thread, right?
Yeah.
So it's just,
Well,
it's
the
in
VM
effect they're
manager-
coroutines, right?
Yeah,
You're just
right.
calling
Yeah.
this other thing and changing the stack pointer. And that's very common. A lot of the papers from the field date from the days before multiprocessors, and a lot of the literature talks about things in those terms. But if you go into the situation where you have multiple underlying, you're using the OS to manage your threads, and presumably because you have a multiprocessor underneath, then a lot of these techniques apply, but you have to also insert the appropriate synchronization things. I'm going to leave almost all of that stuff to a separate talk on dealing with concurrency, because it's really hairy in many places, and it just complicates everything. So it's easier just to present it all in one go. As here are all the things you have to think about when you go multiprocessor or use the underlying OS threads.
Is it possible that when the threads are advanced, the memory got strained because you execute some instructions and those instructions actually use memory?
Sorry, the thread got advanced
It
and
says all threads are advanced until they suspend themselves, right? And what if when during the advanced then you drain the memory? Like, there's some instruction that allocates a lot of memory. Is it possible?
well, so at that point, what you would have is a safe point before an allocation, right? Because you're writing the allocator or you're omitting the allocator, and it can test at that point, just before you're about to allocate,
So
whether this guy's supposed to suspend.
Every instruction that means an allocation has to be checked.
Well, they're not that common. News are not that common. And in fact, there's another technique which we'll describe in the concurrency thing, which is a common technique in a multiprocessor system is you allocate for each thread its own private allocation buffer, and it allocates out of that. So it can make progress in there without actually having to consult the world outside. That solves some of these problems. Okay, you also need to find routes on the stack. So you need to have some way of scanning the stack and finding the things that are stored in the stack frames as to whether they're pointers or hoops if you have a tagged system. So if tagging is used, then typically what will happen is in each stack frame there's some region which will all contain some uniform dense number of oops, the tagged pointers. Because you're writing the compiler, you can manage your own stack, and so when you do that, you can simplify the problem and not having to scatter all the pointers over everywhere. But either way, you need some way of knowing within a particular stack frame where the pointers are. You can keep that information off inside structure if you like. Typically, a list of descriptors tagged at the end. Tacked onto the end of the code of the end method, reachable by some data structure. That might be one way of doing it. Or you stick a pointer to that thing in that block after each call site, right? Because you're walking down the stack anyway, so you can find the calls corresponding to the stack from the return addresses. If immediately after the call you've got some handy data that describes the GC state, it's right there in your hand. So if your language allows you to specify literal objects, i.e. GCable objects in the code, you may choose to emit those things as literals in the code stream. Usually if you're building a word up, you don't get to do that. You can load a word from a side table, but if you're doing assembly of from immediates, usually there's a piecemeal bit fields in the instruction stream. And if you go down that path, well, then you have to bite the bullet and emit into a side table where those instructions live, emit them in a very, sort of consistent manner, and have a piece of code that knows how to look into those instructions, extract the bit fields for the corresponding object pointer, and then be able to rewrite them back. Another thing which is not so bad on a green thread type system. It gets somewhat hairier if that code can be running, because then you somehow have to suspend that thread while it's doing while you're doing the rewrite. So there's a couple of ways of addressing that. Hopefully none of this. If you don't emit code pointers in as immediates, then you don't have this problem. So that's all I'm going to talk about this time. In a week, I think, after the tagging exercise is done, you'll be off writing your own simple JIT for Feeney in your own VM. And some of this stuff will be necessary. You won't need the very fancy stuff. And next week we'll talk about even fancier stuff that you won't need, but you should know about stuff because you're going to need it for later when we use a VM toolkit. But for now, the exercise in a week is going to be, build one of these and make it work. Okay, any questions? Thank you.